The main purpose of this section is to look at how to estimate the probability of success, and then also to make inferences about the probability of success in terms of the population value. To do this, we need to have an introduction to maximum likelihood estimation. Many of my students, many of my readers of my book have already seen maximum likelihood estimation before. So if this happens to be you, just think of this as a brief review. For those of you who maybe have heard of it but don't know exactly what it is, or for even those of you who've never heard of it before, the purpose of this section is to give you the introduction to it, show you a little bit of the math, but also show you some intuitiveness behind maximum likelihood estimation. We will use maximum likelihood estimation almost throughout my entire book, my entire course. Okay, so this corresponding material is actually found in Appendix B of the book. Let's go back to the example where we're looking at trying to understand the success or failure of a field goal. In particular, we're interested in the probability of success for a field goal. And so we're going to, once again, let Y denote a success for a 1, a failure for 0. And we're going to model Y with a Bernoulli distribution. Our probability mass function then looks like this. The probability Y is either equal to 0 or 1, which we just denote by a little y, is pi to the y times 1 minus pi raised to the 1 minus y power. Pi is that probability of success. This is what we're after. This is what we want to estimate, this pi. Now, to estimate this pi, suppose we're interested in a number of field goals that have similar characteristics about them. Maybe, for example, they're all 40-yard field goals. And so what we're going to do is take a sample of field goals performed at this particular distance. The first sample value is going to be denoted as y1, where this could be 0 or 1. The second one is going to be y2, and the nth one will be, let's say, y sub n. Now, given then, so maybe we go out and take this sample. Maybe you're actually performing the sample yourself. Maybe, let's say, maybe n's equal to 10. You kick 40 field goals. And so then you observe the results of success or failure equated to a 0 or a 1, or a 1 and a 0. And we have then this resulting data. Now, given this data, we're going to find what's called a likelihood function. And all that a likelihood function does is a mathematical function that measures the plausibility of particular values of pi. Maybe pi should be 0.1, maybe it should be 0.2. Measures the plausibility of particular values of y given what you've observed in your sample. And so we symbolically denote this in a mathematical form as L for likelihood of pi, and then the vertical line there is similar to what you've seen when you talk about conditional probability. It means the word given. Given my observed data, here's my likelihood function. And all it is this: the probability that my random variable y1, representing what could happen on that first attempt, the probability that y1 is equal to whatever it was observed, 0 or 1. And then multiplied by the probability for y2 all the way down to, keep on multiplying by the probability down to y sub n. We can write this more conveniently using a product notation. So I take the product from I equal 1 to n of the probability y sub I, capital Y sub I, is equal to little y sub I. Now, sometimes I will have students who have not seen this kind of a product notation before, and this is basically the equivalent, I guess, the multiplication equivalent to summation notation. So all of you should have seen something like this. Suppose we have the sum from I equal 1 to n of the probability capital Y sub I is equal to little y sub I. This would be the probability y sub 1 is equal to little y sub 1 plus, and we keep on going all the way down to the nth value. Now, instead of using sums, we use a product, and it's denoted by an uppercase pi letter. This has nothing to do with the pi probability of success, though. Okay, so what is each of these? What are each of these probabilities? Well, using our Bernoulli distribution, we take pi, the probability of success, raise it to the y sub I power times 1 minus pi raised to the 1 minus y sub I power. And again, we're taking the product over our entire sample. And so what this means then is that I have pi raised to the y sub 1, 1 minus pi raised to the 1 minus y sub 1 times, and I do the same thing for y2. And I keep on going all the way to the nth. And I'm not going to write it all out. I'm just going to say the nth there. Okay? Now, what you've learned in an algebra class is that, if I have, let's say, something like a raised to the b power times a raised to the c power, this is a raised to the b plus c power, we're going to apply that same idea here. Notice how I have pi raised to the y sub 1, I have pi raised to the y sub 2, I have pi raised to the y sub n. So what I can do is I can combine all these and add the corresponding exponents. And so in other words, I have pi raised to the sum of all these y sub i's from I equal 1 to n. Similar, notice I have 1 minus pi raised to 1 minus y sub 1 power. I have a 1 minus pi raised to the 1 minus y sub 2 power. I just combine all these things corresponding to what's in the exponent. I sum those up. And so this is then what I'm left with. Now we know that the sum of the y's on our previous notation can also be represented by W, the number of successes. So now I'm left with, for my likelihood function, pi raised to the W power times 1 minus pi raised to the n minus W power. And again, what this likelihood function is representing is, given your observed data, in this case it's going to be the number of successes, what are plausible values of pi? And the way that the likelihood function works is that the larger the likelihood function is, the more plausible the value is for pi. In other words, the value of pi that maximizes this likelihood function is the most plausible, and that's what you should use for your estimate. That's called a maximum likelihood estimate. Okay, so let's put some data in here. Let's say I do observe 4 successes out of 10 field goals, 10 trials. So what I can do with my likelihood function is, let's say that pi is 0.2. So I'm going to plug that in there to the 2 different spots where you see a pi. Plug in the W of 4, plug in the value for n as well, and I get a likelihood function evaluates to 0.000419. I can do the same thing for pi equal 0.3, pi equal 0.35, and so on. And what you'll see is, if you keep on doing this, the largest possible value that likelihood function ends up being is 0.00194. And so what that means is that my maximum likelihood estimate, how about I just abbreviate with MLE, is 0.4. That is the most plausible value for pi given this observed data. Okay, so that's the mathematical way to think about this then. Now, an intuitive way to think about it is, okay, if you make 4 out of 10 field goals, your observed proportion of successes is 0.4. And if I had to somehow estimate what the true value of my probability of success is for all the field goals I could attempt from the same distance under the same circumstances, well, it seems to make sense that why don't I just estimate it with 0.4? And so that's nice how that maximum likelihood estimate corresponds to our intuitive feel for, well, what should I estimate pi with given this sample? Now, let's talk about how we can do some of these calculations in R so that we can get more used to doing calculations in R. So I'm going to come back over here to my tin editor, and I'm going to actually make this change. This will be updated on my website. So I have 4 successes and trials. So I create objects representing those numerical values. And then I'm going to look at, let's say, particular values of pi, like what we saw in that table. And then to find my likelihood function, I'm going to create an object called LIK, for lack of a better name. It's going to get the results from, take pi raised to the w power times 1 minus pi raised to the n minus w power. The way that R operates on these calculations is it says, okay, this pi has a number of different values in it. So what it's going to do is repeat these calculations for every single value of pi. And then I'm going to summarize the results in a data frame. So let's go ahead and do that. And here's basically the numerical results that we saw in that previous table. Let's now look at a graph of the corresponding likelihood function. Before we actually look at the code, let's actually look at it in my notes. And so on my y-axis, I have the actual likelihood function. On my x-axis, I have the possible values of pi. And we can see that where this function is maximized, I mean where it gets to the highest point in this plot, corresponds to pi equal 0.4. So that's why this is called my maximum likelihood estimate. It gives me, again, the most plausible value of pi given my observed data. So now to do this plot, I can use what's called the curve function. This curve function is explained in my Appendix A, but real briefly, let's just go over it again. We'll look at a very simple case before we get to the case that's in the actual notes. Let's say I want to plot this particular function. Y is equal to x squared. And so, the way that you would normally do it, the way you were taught long ago, is you come up with a whole bunch of values of x, plug it into the equation, you get values of y out, then plot the xy coordinates on a plot, draw a line that connects all the points that you've drawn, and voila, there you have your plot. And that's essentially how the curve function works. So if I do curve, EXPR is an argument that stands for expression. What's my mathematical expression I want to plot? I want to plot x squared. Okay? And on what values do I want to plot it? Oh, let's say from -3 to 4. So what I'm going to do is I'm going to combine together the numerical values -3 and 4 with the xlim argument that's also used in the plot function. It says let's begin at -3, let's end at +4 for x. And let's just make it a nice color so it stands out. How about we make the line that's going to be plotted red? So if I go ahead and run that code on another monitor that I'm looking at right now, my window opened up, and here's my graphics window. On my y-axis, I have y is equal to x squared. My x-axis have possible values of x, and so we can see, for example, when x is 0, x squared is 0 as well. And so there's my plot. And so what R actually does, by default, it will use 101 different possible values of x between -3 and 4, evaluate it, plot it, and then essentially connect the points, which you don't actually see, but connect the points with a straight line. And since there's so many points there, you don't see that. In fact, it's actually not a perfect curve. Okay. So in this particular situation then, let me just make that small change. What I need to plot is my likelihood function. Now the way that the curve function works is that whatever you have on the x-axis needs to be in this mathematical function that you use for the EXPR argument. So because pi is my x-axis, I need to replace pi with x. So EXPR, x raised to the w power times 1 minus x raised to the n minus w power. I'm going to go from 0 to 1 my x-axis because pi is the probability of success. It has to be between 0 and 1. My x-axis label, I'm going to do something a little bit fancy. I'm going to put the Greek letter pi on it. The way I can do that is to use the expression function and then actually pi as the as the term that tells R, okay, put the actual Greek letter pi there. Y-axis label as well. I'm going to put a horizontal line at 0 on my plot. And so here we go. And let me find my plot. Here's the likelihood function that we just saw. Okay, let me get back to my notes. Now, very often, so that we don't mistake the true value of pi with its corresponding estimate, what we will do is whenever we're talking about our estimate, which is actually a statistic, we're going to put a little hat sign or the caret sign on top of that pi. So my maximum likelihood estimate pi hat is 0.4. Now there's actually a general mathematical way that one can use to find the maximum likelihood estimate. We won't have a specific occasion where we will actually go through the mathematical details on our own. R is going to have automated ways to calculate maximum likelihood estimates for us. But still, at least once here, it is good for us to go through the mathematical details so that you can see it. So to find the maximum likelihood estimate in a general manner, this almost always works, we can do the following. We can find the natural log of the likelihood function. So log in this class will always mean natural log. We can take the derivative of the log likelihood function with respect to the parameter that we're interested in this case pi. Then we can set our derivative equal to 0, solve for pi to find the maximum likelihood estimate. This will always work except for in particular in some unusual occasions, depending upon the actual probability distribution you're working with. So for our field goal kicking example, our log likelihood function is as follows. I take the log of pi raised to the w times 1 minus pi raised to the n minus w. Now we work with some properties of logarithms that you've seen in an algebra class before. So for example, if I have log of a times b, this is log of a plus the log of b. Also, if I have, let's say, the log of a raised to the b power, this is equivalently b times the log of a. Okay, so in this particular case, then our expression here simplifies. I can basically kind of draw a line there. Now I have log of pi raised to the w power plus log of 1 minus pi raised to the n minus w power. In other words, apply this idea there. Now, since I have some stuff that's in the power, I can move it outside the log, and so in the end I get w times log of pi plus n minus w times log of 1 minus pi. Okay, so next we find the derivative with respect to pi, and we get w over pi minus n minus w over 1 minus pi. We set that derivative equal to 0, solve for pi. You can go through the algebra on your own, and I get pi is equal to w over n. So we can say then more formally, my maximum likelihood estimate in general for any w, for any n, is pi hat is equal to w divided by n. In other words, number of successes divided by number of trials. Again, think of how intuitive that is. Now, if you want to know more about maximum likelihood estimation, especially some of the mathematical properties about it, I have taught an Introduction to Mathematical Statistics course before, and I do talk about that, or I do talk about likelihood functions and maximum likelihood estimation in that course. You can get my corresponding notes and corresponding videos available from chrisbiller.com. Now, maximum likelihood estimators have some very, very nice properties. So first of all, think of our maximum likelihood estimator in general, this pi hat, as a random variable, because it's going to vary from one sample to the next. And as a random variable, as you might expect, it's going to have some kind of probability distribution associated with it. You know, how often are we going to have pi hat equal to 0.1? How often are we going to have pi hat equal to 0.2? It's going to have a probability distribution with it. Now, with maximum likelihood estimators in general, there are 2 or 3 main properties that are very, very nice with them. First of all, if you have a large sample, a maximum likelihood estimator has an approximate normal distribution. So what that's going to do is quantify what are likely values of pi hat. Again, think of pi hat now as a random variable, not a particular numerical value that we've already found as 0.4. Also, for a large sample, the expected value of our estimator, in other words, the mean, is the parameter that you're trying to estimate. That's great. So what I expect, let's say pi hat to be on average for a large sample, should be approximately equal to the true value of pi, that true probability of success in the population. Also, I also will have a way to get the variance of this estimator as well. Now, this variance of this estimator gets to be a little bit more complicated. Again, I'm not going to have a particular situation where I'm going to expect you to find this variance in a mathematical derivation way, but you do need to know what the actual setup is, let's say, for that variance. So my estimated variance, so it's an estimate, because I'm saying estimate, that's why I have a hat on top of the var part of it. And if we just think of like in general, a maximum likelihood estimator, not necessarily the probability of success, but a general maximum likelihood estimator, call it theta hat, the Greek letter theta, which is trying to estimate a parameter in our population called theta. The estimated variance of theta hat is equal to the following. Put a negative out in front. Then you find the expected value of the second derivative of the log likelihood function, where you treat now the observed data as random variables. Take the second derivative with respect to theta, then invert it, and then wherever you see a theta, replace it with a theta hat. So it's quite the process there. And this estimated variance, this is the estimated variance for a large sample. Okay? Well, why is this all important to know? These properties that we just saw. Well, what this is telling me is that I can quantify with probabilities what are likely values of theta hat. This is going to allow us to make inferences with a certain level of accuracy from our sample to our population. Just like in your very first stat course where you looked at, let's say, making inferences about the population mean, call it mu, using the sample mean y bar. Okay, you wanted to make inferences. And what did you do? You did hypothesis tests. You did confidence intervals. We can do the same thing here with any maximum likelihood estimator. Now, since we have this normal distribution property where we know the mean, we know the variance, and this all works if you have a large sample. Now, this large sample, I don't have a specific definition of, if your sample size is greater than or equal to 30, this works. It depends upon the particular situation. Also, for those of you, especially the statistics majors, or those who have a statistics degree who are watching this video, you might want a more mathematical definition of what I mean for a large sample here. Well, here it goes. I can say the square root of n, where n is my sample size, of times theta hat minus theta, converges in distribution to a random variable we're going to call it a, where a has a normal distribution with mean 0 and a particular variance, we'll call it var of theta hat. This is something that's sometimes introduced at the master's level for stat majors. At the PhD level, you actually typically will always do the actual mathematical proof of why this is true for any maximum likelihood estimator. And so this is what I mean by a large sample. Okay, let's now apply this to the field goal kicking example once again. So I have my log likelihood function as what we've seen before. I'm going to take the first derivative with respect to pi. So for example, this w times log of pi there ends up being w over pi. Then for the other part there, I get n minus w over 1 minus pi. Take the second derivative. Now I have negative w over 1 minus pi squared. Where does that negative come from? Well, you're taking the derivative of 1 over pi. That's where it comes from. And then also I have negative of n minus w over 1 minus pi squared. Okay. So to find then this estimated variance here, let's look at, first of all, this expected value portion that's right inside of there. So I take my result, and actually I'm going to, let's say, factor out that negative sign, just so that we don't make a mistake. Okay. And I'm going to take that and actually put it right in there. Okay. So that's step one. Step two, what I'm going to do is find a common denominator for these two fractions inside this expected value. Step three, I'm going to multiply out this polynomial, 1 minus pi raised to the squared, raised to the 2 power. Multiply it out. Step four, still with inside that expected value, I'm going to cancel out some terms. And then step five, I'm going to move this expectation inside of all the components there. Of course, the denominator, this pi squared times 1 minus pi raised to the 2 power, is a constant, so I can factor that out. This I can move the expected value then into the numerator. So I have expected value of w. Then I have minus 2 times pi times expected value of w plus n times pi squared. Okay, we know what the expected value of w is n times pi. So let's go ahead and plug that in there. And that's what I do there. I have some things that simplify so that this part here simplifies with that part. And so now I'm left with a negative n pi squared there. I can factor out n pi in that numerator. So I'm left with n times pi times 1 minus pi all over this pi squared times 1 minus pi squared again. Notice this cancels out. And so this is what I'm left with. So now what I can do is I can plug that in to this expression right here. And remember, of course, we had originally had that negative. We moved that out just so that we didn't make a mistake. And so that negative then cancels out with a negative there. I invert it. I also, wherever I see a pi, I put a pi hat. And now here is my estimated variance for my maximum likelihood estimator, pi hat. It's pi hat over 1 minus pi hat over n. We will make use of this very shortly in another subsection of the notes. If you like more mathematical details, a very common mathematical statistics book is Cassell and Berger. They go through this on page 474 of their 2002 edition. Also a PhD level book about proving the asymptotic normality of maximum likelihood estimators, or in other words, what happens with a large sample, is this book by Ferguson that I really like. So that concludes in this subsection of the notes.